And a happy Thursday. Happy Physics Day. We're doing physics today. Today we look at work. We get back from spring break. It's also another physics day. We look at center of mass. Starting with work. Work is the amount of energy expended when a certain force is used to move an object a distance. We're going to be very limited in this course. We are only going to be dealing with straight lines. Specifically, we're moving it along like an X interval or up against a Y interval. Work gets much more interesting in Calc 3. So we have two scenarios. Constant force and a variable force. So we're applying constant force to move some object d units. Work is simple. It's just force times distance. Standard units for work, what is it? It's the joule, right? Work is energy. Another common unit for work is the calorie. It is very rare, however, that the force is constant the entire time. Right? It usually varies. Your force is now variable, and it depends on position. Work done to move an object from an initial position x0 to a final position, let's call it xf, x1, doesn't matter. Then the work done is the integral over that interval of the force. Right? The idea behind this is you break the, what do I want to call it, the quote unquote trip. Right? So you're breaking the movement of the object up in small enough intervals where the force can be approximated as constant over that tiny interval. And then you sum up the works, right? So in that one tiny interval, just be the constant force times whatever that distance is, right? Then you do another interval, the force times that distance, right? Then you do the next interval, so on and so forth. Turns out that's a Riemann sum. And you just take that limit now as the number of intervals increase to infinity, and you get the integral, and that's how you get this. Still fairly straightforward. Very common type of problem that we deal with is a simple spring. It's going to be a single spring. We're ignoring any kind of friction. Right? We're not even going to let it oscillate. That is different. We're not even going to do double springs. Right? So there's literally just one simple spring. Springs are governed by Hooke's law. Hooke's law states that a spring is going to exert a restoring force whose magnitude is proportional to the spring's displacement. It has opposite direction. Right? So if you're stretching a spring, it's going to exert a restoring force to compress it back to its natural length. The magnitude of this force is proportional to how much it's already been stretched, right? And then obviously compression is the same thing. F is proportional to x, meaning that F is equal to k times x. K is a constant of proportionality, in this case, known as the spring constant. Right? Every spring has its own constant. Sadly, the only way to determine what that constant is through experimentation. Spring has natural length of 10 inches. 800-pound force stretches the spring to 14 inches. We're going to determine how much work is done in stretching the spring from 10 to 12 inches. And then we'll also determine how far beyond its natural length a 1,600-pound force will stretch this spring. Now, we already know that restoring force is going to be proportional to its displacement. So it takes 800 pounds to stretch the spring to 14 inches. What would the displacement be? Four inches. Spring constant here would be 200-pound inverse inches. So the magnitude of our restoring force given by 200x. Now we want how much work is done in stretching the spring from 10 to 12 inches. Our force is variable, right? It depends on how far the spring's been displaced. We're going to have an integral. Integrating 200x dx. From 0 to 2. Right, 10 inches is its natural length, so we take that as 0. Well, this is a really simple integral to evaluate. Get 100x squared. 2 squared is 4. So 400. And what would the units be? Wouldn't it be pounds? Pounds is force. It's not joules because we're not in standard. Do you know what the joule is?
Times inch.
Joule is a Newton meter. So for here, we're going to have the inch pound. With a pound inch, doesn't matter, but for some reason, the empirical, they'd like to say it's the foot pound as its measure of energy. And that's a hyphen, not a minus. So 400 inch pounds of work. How far beyond its natural length will 1,600 pound force stretch the spring? Right, just solve for x in the Hooke's law. So what would x be? 8 what? 8 inches. So 8 inches beyond its natural length. So the spring would be 18 inches. But of course, the question was asking how far beyond natural length, so just 8 inches. Takes 21,714 pounds to compress a coil spring assembly on a New York City Transit Authority subway car from its free height of 8 inches to its fully compressed height of 5 inches. Coil spring assembly is compressed by 1 inch. So the question is, how much work did it take to compress the assembly the first half inch? And then how much would it take to compress it the second half inch? And round all answers to the nearest inch pound. Well, dealing with springs, so it's going to be governed by Hooke's law. Restoring force is proportional to displacement. £21,714 is going to equal, what is the displacement? So K is 21,714 divided by 3. Spring constant here is 7,238 pound inch inverse. Magnitude of the restoring force will be given by 7,000 238x. How much work is it going to take to compress the assembly by a 1/2 inch? What would the limits of integration be? Close.
Yes, 0 to 8.
And I agree 0. So you said a 1/2. Why 1/2? Right, but is it being stretched or compressed? So it'd be 0 to negative a 1/2.
Any difference?
In the calculation, no. Because it's going to wind up being x squared. But physically, this is what it's doing. What was 1/2 of 72, 38, 36, 19? Times a quarter. To the nearest inch pound, what does that give us? So it takes 905 inch pounds to compress it the first 1/2 inch. Compressing it the second 1/2 inch. What would the limits of integration be? That'd be what? 1 minus a quarter, so it'd be 3619 times 3/4. I want the nearest inch pound. So it only takes 905 inch pounds to compress it the first 1/2 inch. Compress it another 1/2 inch after that takes another 2,714 inch pounds. Right. Does that make sense? It does, right? If you've ever tried to compress a spring, the more you compress it, the harder it becomes, right? The more work you have to exert. So yes, that makes sense. By the way, same thing is true for stretching. Enough about springs. When a particle of mass m at the point x0, or when a particle of mass m is at the point x0, it is attracted toward the origin with a force whose magnitude is k over x squared. This is known as an inverse square. It's a very common type of force. Gravity is an inverse square. Electric force is an inverse square. Magnetic force is an inverse square. Light intensity, I believe, is also an inverse square. If the particle starts at rest at x equals b and is acted on by no other forces, find the work done on it by the time it reaches the point x equals a, and we may assume that a is less than b and they're all positive. Right. Right, so our point mass. Sitting right there. There's an attractive force being acted on it. That pulls it towards the origin. And the magnitude of that force, given by k over x squared. Right. The question is, how much work is exerted on the particle to get it to point A? What are the limits of integration? And what are we integrating? X over x squared? Okay. So what's the antiderivative? Oops.
would give you a negative work.
This work is negative. Work can't be negative. Negative work means that you're getting energy for moving. So what's wrong?
You should put an absolute value on the info. I realize you probably want to say limits of integration, but
In physics, you can't just go, oh, I don't want it to be negative, so let me just do absolute values. Sadly, no, that's not how physics works. So the constant is not going to be negative because we're dealing with magnitude. But it does involve a negative. Because it's going to the left, the force is actually negative k over x squared. Which now is going to have the same effect as switching the limits of integration. Right? Because remember, if you multiply an integral by a negative, you can get rid of the negative by flipping the limits of integration. I'm just going to leave the limits as they are. So that becomes k over x from b to a. Right? Yeah, and then it becomes k over a minus k over b. Right? Or k times b minus a all over ab. You caught it before I could ask. With these types of problems, you should always examine your answer to see if it makes sense. The first answer didn't make sense because the work wound up being negative. That's why the a less than b was important. Use Newton's second law of motion to show that the net work done by a force F of x in moving an object of mass m along the x-axis from x1 to x2 is W equals change in k, where k represents the object's kinetic energy. What does Newton's second law of motion say? Force is mass times acceleration Is that correct?
All the forces.
Technically, yes, total force is mass times acceleration. But I'm ignoring that for right now. We did discuss this in my Calc 1. This is not technically correct. Newton made a fatal flaw. He assumed mass was constant. Mass is not constant. Einstein came around and said, mass is actually a function of speed. The faster you move, the more mass you have. Yes. It's E equals mc squared, right? It's the same thing. Right? Because the faster you move, the more kinetic energy you have. So the closer the speed of light you travel, the more mass you have. Which is why you can never actually hit the speed of light. Particle of mass at the speed of light would theoretically have infinite mass. If it had mass, it didn't travel the speed of light. They may have gotten it really, 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 really close. That's why the only object that can travel the speed of light is light. The photon is the only massless particle that we know of. Maybe they found another massless particle. That's possible. So if we're taking relativity into account, what's this change in momentum? Now, for all intents and purposes, and this is what we did in Calc 1, we did a problem where we showed that for essentially low speeds, change in momentum breaks down to ma. Because everyday applications, you're not even traveling a fraction of a percentage of the speed of light. So your mass can be considered constant. And then you get ma. Momentum is mv. Right, mass times velocity. What is kinetic energy? Right, so we're going to keep that in mind as well. We are going to make the assumption here that we are traveling at unrelativistic speeds, which would make Newton's second law apply. Kinetic energy. So work. x1 to x2. The force dx. This is where things get fun. Mass is a constant, so factor it out. A. That's a problem. I'm gonna write it as dv dt. And then by chain rule, write it as dv dx times dx dt. Acceleration is derivative velocity with respect to time. So that's why I'm using dv dt. Because I want to use chain rule to get dx, right? The derivative of something with respect to x. That's my ultimate goal. But dx dt is just v, right? It's velocity. This is u sub. Let u be v. Du is then dv with respect to x and then dx. That's 1/2 mv squared, x evaluated from x1 to x2. But remember, we just wrote velocity as a function of x. Oops.
You're allowed to put the square there.
Yeah.
Even though it's a function.
Yeah, it's common notation. Right, because you have sine squared of
Well,
x.
I mean, I've seen it there. I thought it
It's
was
also, you can also do it with log. Log squared of x means log of x all squared. So in general, f squared of x just simply means f of x all squared. But you just have to be careful because just like with the trig, if you raise that to the -1, that does not mean 1 over. It means the inverse function. So that's the only caveat. Well, v of x2 would be final velocity. V of x1 would be initial velocity, so just call it v2 and v1 respectively. That's final kinetic minus initial kinetic. Which is change in kinetic energy as desired. So what this says, you can also think of work as change in kinetic energy. In fact, there are, generally speaking, two methods to solving motion problems in physics, in classical Newtonian mechanics. The first method is what you learn in intramechanics, force analysis. Second method is by converting it to an energy problem. And then you do energy analysis instead of force analysis. Converting it to an energy problem is way easier. Especially when you start to deal with friction. Newtonian mechanics is a junior level physics course, though, so unless you're a physics major, you won't have to take it. If you're a physics major, I feel sorry for you because that was one of the hardest courses I've ever taken. Quantum was easier than Newtonian mechanics. Find the work required to lift a 1,000 kilogram satellite to a circular orbit of 29,409 kilometers. Okay. We are again going to be making a simplifying assumption that we are dealing with non-relativistic speeds here. So we can ignore all relativistic effects. This allows us to use Newton's law of gravity. Love Newton's law of gravity. I think we also did this in Calc 1. Do you remember what it is? Oh, you make me sad. What is it? No, that's force due to gravity. Right, on the Earth, m times acceleration due to gravity. So that's essentially your weight. F is G big M over R squared. G is the universal gravitational constant. Big M and little m are the masses of the two objects. Typically, we let big M represent the more massive object. And R is the distance between the objects. What this law says is every object of mass exerts a gravitational attraction on every other object of mass. Since Aiden made me sad, he's going to be the one I pick on for this. This means that everyone in this room is attracted to Aiden. Unfortunately for him, that also means that every object in this room, the tables and the chairs, are also attracted to him, which could be quite dangerous to your health. Right? One scene in particular always comes to mind when I think of Newton's law of gravity, and that's that one Family Guy scene where Brian throws stuff at Peter and it starts to orbit him. While that is clearly a gross exaggeration, it is based in physics. Right. So the question is, if Aiden is exerting a gravitational attraction to all of us, why aren't we flying towards him right now? True, but I don't see you flying off into space. Every force, yeah, every action has an equal and opposite reaction. That is certainly true. But again, I say, then why aren't you flying off into space right now? Right. Yes, I mean, you have other gravitational forces that are canceling out, but the most important thing is the gravitational attraction of the Earth dominates. I'm pretty sure the Earth is way more massive than Maiden. Can safely make that assumption. If not, we're all in trouble. So that's just like a little cool physics thing. So whenever you're feeling down, just remember everyone's attracted to you. This is what we're going to be using to calculate the work. So this is the force we have to overcome. We have to overcome Earth's gravitational force being exerted on the satellite. Yeah. Right, so little m would be 1,000 kilograms for us. Then we have G, the mass of the Earth, right? So in astronomy, that is the symbol for Earth. All over r squared, right? And again, r is the distance. That's the 1,000. That's the mass of the satellite. For right now, I'm going to do the calculations using G and ME. I'm just going to call that symbol E. I'll worry about plugging in their approximations at the end. Work. Integral. And what are the limits of integration? How'd you get 0 to 29,409? Right, that is a common misconception, which is why I always ask it. So that'd be the surface of the Earth, right? There's its center. Doesn't have a distance of the Earth's radius. Huh?
I mean, that and the other.
Yeah. Because what are you being attracted to? You're being attracted to the center of the Earth.
Oh, I see why you put that as the radius, but you also put it like when you say you have a circular orbit of like whatever amount that includes
You have
the
to.
depth. Yeah.
So when we deal with orbits, they always talk about distance from the surface. So we have to add the radius into whatever distance they give us.
Oh, I see.
Right. Again, because the attractiveness is not to the surface of the Earth. It's the center of the Earth.
So the
Right. That's why you fall down a hole.
so the limits are R Earth to R Earth plus
Right.
20,409.
So the limits would be the radius of the Earth to the radius of the Earth plus that 29,404. Which I think I'm going to represent as something different. Ah, 409. I think I'm just going to represent it as CO, circular orbit, just so I have to keep writing 29,409. Again, very common practice in math and physics when you're dealing with something that you're going to be running a lot. Just give it a variable. Because we are by our nature lazy. Well, 1,000 is a constant, right? G is a constant. Since we're ignoring relativistic effects, the mass of the Earth is constant. Right, so all we're left with is that integral. We just need the antiderivative 1 over r squared. Well, that's simple. Just negative 1 over r, isn't it? So we're going to wind up with 1,000 gm of the Earth over radius of the Earth minus, right, I'm flipping the order because it's negative, 1,000 g mass of the Earth all over radius of the Earth plus that circular orbit, 29,409 kilometers. But to the lay person, that means absolutely nothing. Right? Because they just look and they go, what the hell do all those symbols mean? Mass of the Earth. 5.975 times 10 to the 24th kilograms. So we take mass of the Earth to be about 5.975 times 10 to the 24th kilograms.
Two.
I'm seeing 6 times 10 to the 24th. I think the reference I used was a little more precise. That's why I got this. I mean, it's really not going to make too much of a difference in the grand scheme of things. Right, I think I actually looked it up on Wolfram Alpha. That's what it gave me. And I'm seeing on, wow, Wikipedia actually got something right for once. Wikipedia also has 5.9722 times 10 to the 24th. By the way, does anyone happen to know what the mass of the sun is? It's about 2 times 10 to the 30th kilograms. Put that into perspective. That means the sun is about 1,000,000 times more massive than the Earth. Even Jupiter doesn't compare. I think Jupiter is like 10 to the 25. Ten to the 27. So Jupiter's 2 times 10 to the 27. So the sun is 1,000 times more massive than Jupiter. Radius of the Earth. About 6.37 times 10 to the 6th meters. I converted that because I think it typically gives radius in kilometers. But I want meters. The universal gravitational constant. (6.672 times 10 to the minus 11). Yes, gravity is actually very weak. That's acceleration due to gravity. This is the universal gravitational constant. Right. Gravity is an extremely weak force. You overcome it every single day. I just overcame gravity. With, when was the moon landing? The 60s? 70s? It's primitive technology. We left Earth's gravitational field with primitive technology. That's how weak gravity is. So if we plug in all these numbers, and again, remembering that CO is 29,409 kilometers, we find that the work is about 51 billion joules. And I believe it's in the lecture video, I derived the escape velocity for Earth. Something like 11,000 kilometers an hour or something. $11.2 kilometers per second. And again, we achieved that. Two electrons, our meters apart, repel each other with a force of 23 times 10 to the minus 29 over r squared newtons. It is again an inverse square, and that has significant meaning. I think it's some constant times the charge of one particle times the charge of the other particle divided by r squared. That's the repulsion or attractive force, depending on if the charges are the same or opposite. I can't remember what that constant is, though. Might be Coulomb's constant. Right, but it looks identical to Newton's law of gravity. Right, so obviously here they're using that, I think it's Coulomb's constant, and then the charges of the two electrons. That'll be the charge of an electron squared. And that's where they're getting the 23 times 10 to the minus 29 from. Suppose one electron is held fixed at the point 1, 0 on the x-axis, units measured in meters. How much work does it take to move a second electron along the x-axis from the point -1, 0 to the origin? Right? So here's the origin. 1, -1. We have one electron there, and we have a fixed electron there. Right? The reason why it's important for that electron to be fixed is if we went to move this electron to the origin and that wasn't fixed, that would just move. Right? It would just repel that electron. So what we have to do is, since we're moving this to the origin, we have to overcome the repulsive force that the first electron is exerting. Right? Best analogy I can give is when you try to put magnets together. If it's the same pole, they repel each other. North and north repel, south and north attract. So that's that. The magnetic force is identical to electric force, so that is essentially what we're doing here. Where it's like we're trying to push one magnet onto the same pole. That's the force we're overcoming. So we're going to integrate, right? We're integrating 23 times 10 to the minus 29 over r squared dr. What are the limits of integration? I see where you're getting negative 2 to negative 1 from, but they're not negative because r is a distance, and distance can't be negative. So it's actually 2 to 1. Right?
Were we not moving a distance in that problem with 0, A, and B?
Hmm?
Were we not moving a distance in the problem with 0, A, and B? Where you said because we were moving left, it was negative?
That was the force. Right? The force was negative. Oh, are you talking about this here? That should be negative. Because it's a repulsive force. But if you're talking about the actual distance, these are positive. Right? It was only the force that we made negative because the force has the direction. But yes, this should be a negative here because it is a repulsive force. Well, it's just essentially going to be 1 over r squared, right? That antiderivative negative 1 over r. Of course, we have a negative being multiplied by it, so it becomes positive 1 over r times that constant. 2 to 1. Let's see if we can do this without a calculator. Right, everything's in newtons and meters, so the units will be joules. 23 times 10 to the minus 29 over 2. Which is 11.5 times 10 to the minus 29 joules. So not a lot of work is required. Negative 29. That actually makes sense because we're dealing with meters. the repulsive force doesn't really get strong until you get really, really, really close to it. We're talking about like micrometers, nanometers. By the way, what if I changed the problem and I said, what happens as we move the second electron closer to the first and the first is still fixed? What happens to the work? How much work would you need? How much? What I'm looking for is essentially that limit. Q2 is getting closer to Q1. So if that's the case, what's happening to R? To what? What's that limit? It would take an infinite amount of work to actually get the two electrons together. In other words, it's not possible. Does anyone know the four fundamental forces of the universe? It's gravity,
Strong and weak nuclear.
strong and weak nuclear,
Electromagnetic.
electromagnetic. Of the four, gravity is the weakest. And it's not even close. Like you have those three, and like gravity's all the way over here. It's not at the cool kids table. What's the strongest? Well, that's not a force. Strong nuclear, weak nuclear, and electromagnetic. Spoiler alert, it's in the name. Strong nuclear is the strongest of the four. In a sense, it is the strong nuclear force that keeps the nucleus intact. Right? Because remember, the nucleus has protons and neutrons in it. If it wasn't for the strong nuclear force, those protons would shoot each other out of the nucleus and destroy the nucleus. The weak nuclear, in short, is what keeps the electrons orbiting the nucleus. Prevents the electrons from just scattering. And then, of course, you know what electromagnetic force is. I think weak nuclear is stronger than electromagnetic. And of course, those three forces don't play nicely with gravity. Right, that's quantum mechanics and general relativity. They do not play nice together. That's where string theory came from. String theory actually now gets quantum mechanics and general relativity to play nice. The consequence is it requires 9 spatial dimensions to do it. One. And it now says that strings are the building blocks of everything, but these strings are the Planck length, meaning we'll never be able to actually observe them. Because to magnify that much, we'd require the Planck energy, which is the total energy in the universe. Sadly, I don't think we're ever going to be able to verify string theory. Questions on work.
One problem where it was like 0 to 0.5 or something. I was just kind of curious how that would be impeached from that.
The 0 to negative 0.5?
Yeah.
So how much work does it take to compress the assembly the first ½ inch?
Oh.
Right, so that's where the half comes from, and because it's being compressed, it's negative. Right, even though if you don't do negative and you just use displacement instead, you actually will get the same thing because of x squared. Right, but physically, because it's being compressed, it's going from 0 to negative ½ inch.
But then distance, it's always been possible. So that like the only chance.
Distance is positive, yes.
The only chance.
Right, I was confused. I think it's displacement that can be negative. Right, distance is positive. Displacement can be negative.
This is displacement.
Yes.
Okay.
Anything else? Apparently a scan's been activated. That's nice. Excellent. Funny thing is, the more questions you answer in physics, the more questions arise. Answer one question, you get like 8 questions out of that.
One you skipped on Thursday.
Disadvantage of sitting up right up front, I mean. But so obviously when you're done, turn it in and then have a wonderful spring break.